Hello to everyone. Welcome to the course on numerical linear algebra and application. Today we are going to learn 11th module, second lecture, that is lecture number 52 of this course. As we did in the previous lecture, in this lecture also we would like to do some worked out examples so that you will get familiarity for working out the practical example. And once you are comfortable with the examples, you can also write the computer code so that you could able to learn how these iterations would work for a particular system of equations. Now let us look at into the Jordan canonical form of the matrix. All of you knowing very well, Jordan canonical form is one of the important setup in the matrix iterative procedures. So the first and foremost thing is we'll try to find out the eigenvalues of this matrix. Look at this. The matrix is a 3 by 3 matrix and we do expect that 3 eigenvalues. And let's say A minus lambda is equal to 0. That is 2 minus lambda minus 1, 1, 1, 5 minus lambda minus 2, 0, 1, 2 minus lambda. So if you expand this determinant, you will have 2 minus lambda, 5 minus lambda, 2 minus lambda, and yes, 2 minus lambda, 10 minus 7 lambda plus lambda square. So then you do get like this, then you will have the cubic equation lambda minus 3 whole cube will be equal to 0. Therefore, the eigenvalues of this matrix are so repeated, lambda is equal to 3, lambda is equal to 3, lambda is equal to 3. So we get only one different eigenvalue but repeated thrice. Let's see what is the consequence of this. That means we can able to find out only one eigenvector corresponding to lambda is equal to 3. That is A minus lambda I, that is A minus 3i, 2 minus 3 minus 1, 1, 1, 5 minus 3 minus 2, 0, 1, 2 minus 3. That will be equivalent to minus 1, minus 1, 1, 1, 2, minus 2, 0, 1, minus 1. So this is what the A minus lambda I, you get it. Now what we do is, I'll try to reduce this matrix by using the elementary row operations. So what are those elementary operations I do apply? I do apply R2 plus R1 in order to get rid of the changes in the row R2. So you get minus 1, minus 1, 1, 0, 1, minus 1, 0, 1, minus 1. So that is applying R3, that is R3 minus R2. So that is R3 will change as. So minus 1, minus 1, 1, 0, 1, minus 1, that is 0, 0, 0. So last row has become zeros. Therefore, you can write it as, that is A minus 3i acting on x, y, z will be equivalent to 0, 0, 0. So that is minus 1, minus 1, 1, 0, 1, minus 1, 0, 0, 0 multiplied with x, y, z. So it turns out to be 0, 0, 0. So you do get the matrix like this. Minus x minus y plus z will be 0. Y minus z is 0. Thus we will have y is equal to z and x is equal to 0. So this is the relation which we do get it. Now when you write this z is equal to 1, then we will have eigenvector like this. That is v1 is 0, 1, 1. Thus the geometric multiplicity of lambda is equal to 3 is 1, which is different from the algebraic multiplicity. Thus the given matrix A is not diagonalizable. So as we see, the lambda is equal to 3, geometric multiplicity is 1, and which is different from the algebraic multiplicity. So thus the given matrix A is cannot be diagonalizable. Therefore, we can write the Jordan canonical form of the matrix A. So you will have, these are the eigenvalues, and this is the subdiagonal, and rest are all zeros. So you do get what we call bidiagonal matrix. Bidiagonal matrix. To find the matrix P such that A is equal to Pj times of P inverse, we need to find the generalized eigenvector lambda is equal to 3. To find the generalized eigenvectors, that is A minus 3i times of xyz will be equivalent to 0, 1, 1. That is, you will have minus 1, minus 1, 1, 1, 2, minus 2, 0, 1, minus 1. So when multiplied with x, y, z, so this will be equivalent to 0, 1, 1, the system. And you can write it as minus 1, minus 1, 1, 0, 1, minus 1, 0, 0, 0, multiplied with x, y, z. So you do get as 0, 1, 0. So you will end up with the matrix eigenvector like this: minus x, minus y plus z is equal to 0, and y is equal to, that is y minus z is equal to 1. So therefore, we get y is equal to z plus 1 and x is equal to minus 1 and let z is equal to c. So then you will have x, y, z, that is equal to this vector, that is minus 1 c plus 1 c. So which can be written as minus 1, 1, 0 plus c times of 0, 1, 1. So hence we can write this V2 is equal to as minus 1, 1, 0 and V3 is equal to 0, 1, 1. So you get V1. So V2 is known, V3 is known, that is V1. So I want to find out V3. So V3 is nothing but A minus 3i times of xyz will be equivalent to V2. So you get a matrix like this, system like this: minus 1, minus 1, 1, 1, 2, minus 2, 0, 1, minus 1 multiplied with x, y, z. So you get as minus 1, 1 and it is 0. By applying R2, that is R2 plus R1, so you get as minus 1, minus 1, 1, 0, 1, minus 1, 0, 1, minus 1 multiplied with x, y, z, you get minus 1, 0, 0. So by applying R3 minus R1, so when you write this R3 minus R1, you write it, R3 will changes to minus 1, minus 1, 0, 1, 0, 1, minus 1, 0, 0, 0 multiplied with x, y, z will be equivalent to minus 1, 0, 0. So you get ultimately the values minus x minus y plus z will be equivalent to minus 1 and y minus z is equal to 0. Hence we have x is equal to 1 and y is equal to z and z is equal to c. We get matrix like this: x, y, z is equal to 1, c, c, and that will be equivalent to 1, 0, 0 plus c times of 0, 1, 1. Since V1 is equal to 0, 1, 1, thus we have V3 is equal to 1, 0, 0. Therefore, we get the matrix P is equal to V1, V2, V3. And then we can write this P inverse. Once P is known, so getting a P inverse is not very difficult. So that is 1 by AD minus BC, and changing the main diagonal elementaries, and we can do that minors of, that is the minor of first element, minor of second, minor of third, and the transpose of the principal minors will give you the matrix P. So if you multiply this Pj inverse P, that is P is the matrix, the one which we did it 0, minus 1, 1, 1, 1, 0, 1, 0, 0, and J is the matrix, that is 3, 3, 3 and 0, 0, 1, 1, that is the matrix. Then you get P inverse will be like this: 0, 0, 1, 0, 1, minus 1, 1, 1, minus 1. So you multiply this, ultimately you will end up with a matrix like this A. So which is exactly, that is the coefficient matrix as we as we have taken in the beginning. So let us look at some more examples using the Koleski decomposition. So solve the following linear systems using Koleski decomposition. Koleski decomposition is one of the very important technique which uses iterative procedure in solving the system of equations. Look at this. What I have is 4x plus 10y plus 8z. Suppose x is equal to 1, y is equal to 2, z is equal to 3. What will happen? 4, 20, 24. So 48. Okay, this is fine. So it is 10, 52, 52, 104 and 52, 52, 104, 10. So 52, 52, that is 104 plus 10. No, it doesn't satisfy. This one is 8, 52, that is 132, that is 122, 122. Right? No, this is 8, 52, that is 60, 60, and this is no, this will not work. So guessing a solution doesn't work. So what we do is now convert the given matrix equal to this form, system of equations of this form. That is 4, 10, 8, 10, 26, 26, 8, 26, 21, 61, multiplied with x, y, z. So when you multiply with x, y, z, it will give you 44, 128, 214. Now let the matrix, coefficient matrix is like this, that is 4, 10, 8, 10, 26, 26, 8, 26, 61. So the x is x, y, z and the matrix B is equal to 44, 128, 214. So we know that clearly A is the symmetric matrix. So then we will have A is a positive differential matrix, then we will have, that is mod of 4 is 4 and mod of this thing will be, that is 24, 104 minus 100, that is equal to 4, and here also turns out to be 36. Since determinants of the upper left submatrices are positive, so A is a positive definite matrix. Thus we can apply Koleski decomposition of this matrix and we can solve. And we can write this formula HK1, that is Koleski decomposition. If we write HK1, AKI minus summation j is equal to 1 to I minus 1, Hij times of AKJ divided by HII, and HKK will be, that is square root of AKK minus summation j is equal to 1 to k minus 1, H square Kj, and ultimately you get this matrix A is equal to 4, 10, 8 and 10, 26, 26, 8, 26 and 61. So now as per this algorithm, H11 is square root of A11, that is square root of 4, which is 2. H21 is A21 upon H11, that is A21 is 10 upon 2, that is 5. H22 is square root of H22 minus H square 2 to 1, that is under square root, which is 22 minus 5 square, 25, that is 1. And H31 is A31 upon H11, that is 8 upon 2, 4. And H32 is A32, that is A32 minus H31 times of H21 upon H22. So ultimately you will get it 20, that is 6 by 1, which is equal to 6. Then H of 33 is square root of A33 minus H square 31, H square 32. So you get 61 minus 16 minus 36, which is equal to, that is square root of 9, which is 3. And a capital H is, that is H11, H22, H33, H21, H32, H31, 0. So this is the one which you get it by this process, 200, 510, 3463. And similarly H times H transpose is, H is known here and H transpose is known here. When you multiply this, 2 to the 4, 2 5 is 10, yes, 2 4 to the 8, yes, 5 to the 10, that is 10, 5 is 25 plus 1, that is 6, 4 5 are 20 plus 6 plus 3, 26. That is 4 2 is 8. 5 4 is 20 plus 6, 26. 4 5 are 20 plus 36, 56 plus 3. So that is 4 into 8, that is 32. 6 into, no, 4 into 4, that is 16. 6 into 6, 36. That is 52 plus 9, 61. And now Ax is equal to B. So you write it as H times of H transpose is equal to X is equal to B. So you write this and let H transpose X is equal to Y. So therefore essentially we will have Hy is equal to B. So Hy is equal to B means H is that matrix, right? And B is the Y1, Y2, Y3. You get X1, X2, B1, B2, B3. So by this process you will be knowing what is Y1, what is Y2, what is Y3. So Y1, Y2, Y3 are known. Once Y1, Y2, Y3 are known, so 4Y1 plus 6Y2 is equal to 4. This is the equation you do get it, Y1, Y2, 3. So now left, that is the lower triangle transpose of X is equal to Y. So you get 2, 1, 0, 0, 0, 5, 4, 6, X1, X2, X3. You get 22, 18, 6. So this simplifies to, then we will have this matrix, that is 3z is equal to 6, z will be 2, and by the second equation we get y is equal to 6. So therefore you have 2x plus 4y, 2x plus 5y plus 4z is equal to 22, 2x plus 5 into 6, 4 into 2 is equal to 22, this is verified. So then ultimately you will get the matrix X is equal to 8. Therefore we have the solution by decomposition. Composition is equal to X is equal to X1, X is equal to 0.8, Y is equal to 6 and Z is equal to 2. So with these examples, so what we learned is how Cholesky decomposition would work for a particular matrix, and similarly other examples which we did today. So I will stop over here. Thank you very much for listening to my lecture today. Again I will get back to you. Thank you once again. Thank you.